The James Webb Space Telescope, JWST, has revolutionized our understanding of the universe, setting new benchmarks in astronomical research. Its unprecedented technology has not only deepened our knowledge of galaxies billions of light-years away, but also shed extraordinary light on Pluto, one of the most enigmatic bodies in our solar system. By utilizing its highly advanced infrared sensors, JWST has unveiled startling details about Pluto's dynamic geological activity and its complex relationship with its largest moon, Charon. These discoveries challenge long-held beliefs and open up exciting possibilities for future exploration. Even physicist Michio Kaku couldn't contain his excitement, stating that JWST has finally uncovered what NASA may have been hiding about Pluto. The revelations are not only scientifically significant, but also shocking in their implications. So, what is this groundbreaking discovery? Let's explore. Pluto. From planet to dwarf planet. Pluto's journey in the annals of astronomy is as dynamic as the planet itself. Discovered in 1930 by Clyde Tombaugh, it was celebrated as the 9th planet in the solar system. Despite its small size and highly eccentric orbit, Pluto held its position as a planet for decades. However, this status came into question as astronomers discovered more celestial bodies in the Kuiper Belt, a region beyond Neptune teeming with icy objects. In 2006, the International Astronomical Union (IAU) redefined the criteria for a planet, declaring that a celestial body must orbit the Sun, have sufficient mass to assume a nearly round shape, and clear its orbit of other debris. Pluto failed to meet the third criterion, leading to its reclassification as a dwarf planet. This decision sparked debates among scientists and the public, with many lamenting the loss of Pluto's planetary status. Yet, Pluto remains one of the most fascinating objects in our solar system, offering endless opportunities for discovery. Its reclassification didn't diminish its importance. It amplified it, placing Pluto at the forefront of research into icy worlds beyond Neptune. The New Horizons mission, a first look at Pluto. For decades, Pluto was a distant mystery, visible only as a small dot through telescopes. That changed in 2015, when NASA's New Horizons spacecraft conducted a historic flyby, providing humanity's first detailed images of Pluto. New Horizons revealed a world far more dynamic than previously imagined. Instead of a barren, icy wasteland, Pluto displayed an active surface, featuring Sputnik Planitia, a vast, smooth plain of nitrogen ice, towering water ice mountains, some reaching heights comparable to the Rockies on Earth, evidence of a possible subsurface ocean, which could harbor liquid water beneath Pluto's icy shell. The data also indicated the presence of a thin atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. This atmosphere undergoes dramatic changes as Pluto moves closer to or farther from the Sun in its elliptical orbit. The James Webb Space Telescope's contributions. Building on New Horizons discoveries, JWST has taken the study of Pluto to new heights. Its infrared capabilities have detected heat signatures and surface features that were previously invisible. These observations suggest the possibility of localized heating on Pluto, enough to sustain pockets of liquid water beneath its crust. Moreover, JWST has confirmed the presence of complex organic molecules on Pluto's surface and in its atmosphere. These molecules, including hydrocarbons and tholins, form through the interaction of solar radiation with simpler compounds like methane and nitrogen. Tholins, in particular, are of great interest. They are believed to be among the building blocks of life. Pluto's geological activity. One of the most surprising revelations about Pluto is its geological activity. For a long time, scientists assumed that such a small, distant body would be geologically dead. However, New Horizons and JWST have painted a very different picture. Cryovolcanism on Pluto has been confirmed, with icy volcanoes erupting water, ammonia, and methane instead of molten rock. These eruptions reshape the surface, creating features like the smooth plains of Sputnik Planitia. The detection of faults, ridges, and other tectonic structures suggests that Pluto's crust is undergoing constant reshaping due to internal forces. Internal heating, possibly from radioactive decay or tidal interactions with Charon, could be driving this activity. This heating might also sustain the subsurface ocean, making Pluto a candidate for hosting life in its extreme environment. Charon, Pluto's dynamic moon. Charon, Pluto's largest moon, is no passive companion. Recent observations have revealed that Charon has undergone significant geological changes. Its surface features include large canyons and fractures, indicating tectonic activity. Smooth plains, possibly formed by resurfacing events caused by cryovolcanism or internal heating. A thin atmosphere and evidence of complex organic molecules. Like Pluto, Charon may harbor a subsurface ocean or a layer of slushy, partially liquid ice beneath its crust. The gravitational interactions between Pluto and Charon create tidal forces that could generate internal heat, fueling geological activity on both bodies. Pluto's chaotic neighborhood. Pluto doesn't exist in isolation. It is part of a complex system that includes Charon and 4 smaller moons: Styx, Nix, Kerberos, and Hydra. These moons, along with Pluto and Charon, form a gravitationally intricate system. Pluto and Charon are tidally locked, always showing the same face to each other, while the smaller moons exhibit chaotic orbits influenced by the gravitational pull of the larger bodies. Pluto's elliptical orbit adds another layer of complexity. As it moves closer to or farther from the Sun, its atmosphere expands and contracts, with volatile compounds freezing out or sublimating into gas. These changes create a dynamic environment, even in the frigid reaches of the Kuiper Belt. Implications for life and future exploration. The discovery of organic molecules, geological activity, and the potential for a subsurface ocean on Pluto raises profound questions about the possibility of life. Similar environments, such as the subsurface oceans of Europa and Enceladus, are considered prime candidates for microbial life. Could Pluto join their ranks? The study of Pluto and its moons also provides insights into the formation of the solar system. By understanding how these distant, icy worlds evolved, scientists can piece together the broader story of planetary formation and migration. Future missions, building on the success of New Horizons and JWST, could explore Pluto and its moons in greater detail. Landers, orbiters, or even subsurface probes could unlock the secrets of this fascinating system, providing answers to questions about its history, geology, and potential habitability. Pluto's story is far from over. Once dismissed as a cold, dead world, it has emerged as a dynamic and complex celestial body, reshaping our understanding of the outer solar system. Thanks to the groundbreaking observations of the James Webb Space Telescope, Pluto continues to defy expectations, proving that even the smallest worlds can hold the biggest surprises. Pluto, a window into the origins of the solar system. Located beyond Neptune, between the scattered disk and the classical Kuiper Belt, Pluto is a well-preserved relic of the early solar system. Often referred to as a fossil of the cosmos, Pluto holds the key to understanding the processes that shaped our planetary neighborhood billions of years ago. Its pristine condition and remote location make it an invaluable subject for scientists seeking to unlock the mysteries of solar system formation. Pluto's surface and atmosphere have shown remarkable complexity, undergoing changes that defy expectations for a body so far from the Sun. These dynamic characteristics offer critical insights into planetary evolution, including the roles of temperature, radiation, and chemical interactions. Despite its icy composition and distance from the Sun, Pluto's evolution shares similarities with the inner planets, demonstrating that fundamental processes like accretion and differentiation occur across diverse environments. The role of the Kuiper Belt in planetary formation. As part of the Kuiper Belt, a region filled with icy bodies and remnants of the early solar system, Pluto provides a rare opportunity to study primordial materials. The Kuiper Belt is believed to be the source of many comets and other objects that played pivotal roles in shaping the inner planets. Pluto, as one of the largest known Kuiper Belt objects, allows scientists to investigate these remnants in detail. Volatile ices and organic materials on Pluto's surface remain largely unaltered due to the extreme cold and minimal solar radiation. By studying these materials, scientists can refine models of planetary formation, particularly in the outer regions of the solar system beyond the snow line. The snow line represents the distance from the sun at which volatile compounds like water, methane, and ammonia freeze, locking them in place for billions of years. Pluto and Charon, a double planetary system. One of Pluto's most intriguing features is its relationship with its largest moon, Charon. Unlike most planetary systems, Pluto and Charon orbit a common center of mass located outside of Pluto, often leading scientists to describe them as a double-planet system. This unique gravitational interaction provides valuable insights into tidal forces, orbital evolution, and the dynamics of planetary moon systems. The interaction between Pluto and Charon has likely shaped their atmospheres and surface features over time. The gravitational tug-of-war between these two bodies creates tidal forces that influence their internal heat and geological activity. Understanding these interactions helps scientists piece together the puzzle of how moons and planets evolve, not just in our solar system but potentially in exoplanetary systems as well. Geological activity and heat retention on Pluto. For much of the 20th century, Pluto was assumed to be a cold, geologically inert body. Its small size, distant orbit, and extreme environment led scientists to believe that any internal heat would have dissipated long ago. However, recent discoveries have overturned this assumption, revealing that Pluto is far more dynamic than previously imagined. Beneath Pluto's icy crust lies a subsurface ocean, kept in liquid form by a combination of internal heat sources and insulating layers of ice. This ocean exists despite surface temperatures plummeting to around -225 degrees Celsius, a discovery that has profound implications for planetary science. The most significant source of heat is thought to be tidal heating, generated by the gravitational interplay between Pluto and Charon. As the two bodies orbit each other, their gravitational pulls create friction within their interiors, producing heat. This tidal heating not only sustains Pluto's subsurface ocean but may also drive other geological phenomena. For instance, cryovolcanism, where icy materials erupt from beneath the surface, has been observed on Pluto. Regions like Sputnik Planitia, with its smooth, icy plains, provide evidence of recent cryovolcanic activity, suggesting that Pluto is still geologically active. Implications for the outer solar system. Pluto's unexpected heat retention and geological activity have significant implications for other icy worlds in the outer solar system. Moons like Europa, Enceladus, and Titan are also known to harbor subsurface oceans beneath their icy crusts. These oceans are considered potential habitats for microbial life, making them prime targets for future exploration.